Welcome to video 6. Today we'll talk about stabilizing control. And by stabilizing control I mean when the pendulum is here, we want to find the control signal so that we keep the pendulum there and do not fall down. Alright. Here we are in VS Code and we're gonna design an LQG controller. It's a linear quadratic Gaussian. And we will do that by linearize the nonlinear system model in this position here and design for the linear system. We start by loading a bunch of packages. We have the Quanser interface, the control systems package, and the robust optimal control. We define a simulator of the process so that we can linearize it. And here the parameters are the optimized parameters from the previous video. We define the reference point, so this is the upwards equilibrium where the arm angle is pi, the pendulum angle is pi. We have an initial state, x0, and we have an helper function to normalize angles to be between negative pi and pi. Because if we keep turning this several revolutions, the angle will just increase to outside of that range, but this just wraps it into that range. Right, here is a function to linearize the pendulum model. We first call linearize on the dynamics, and that gives us the A and B matrices. Then we linearize also the measurement function and get the C and D matrices. We can look at that system. It's a state-based system. It has 4 states, 1 input, 2 outputs. So we output the arm angle and the pendulum angle. All right. To do the control design in discrete time, we discretize that system using the continuous to discrete C to D function, and now we get another state space model with a particular sample time here. Right, for the LQR problem, we need 2 cost matrices. So we penalize very heavily the deviations in the arm angle. We penalize somewhat heavily deviations in the pendulum angle, and then the angular velocities not so much. And then here we have some tuning parameter to penalize the control action. All right, and then we design the Kalman filter. We do this using kind of the result we got from estimating the covariance matrices in the previous video. Then we package all of this into an extended state space, and the reason we use the extended state space object here is so that we can make use of the LQG problem type. And here we say that C1, this is the output matrix for the controlled outputs, and that just says that we care about all the states, even though we can only measure 2. And this says that all the states are affected by dynamics noise, even though we only have 2 inputs. And the reason we do this is because we have manually kind of selected, built the covariance matrix in the correct shape here. All right, then we package the system and our matrices into an LQG problem. And when we have done that, we can ask for the LQR gain. And we could also call LQR like this. If we had liked, we could pass the system Q1 and Q2. So that would be the traditional way of doing it. But now we have packaged everything into this helper struct here. And so we can call LQR and we can call Kalman here. And I say direct. That's because I want my resulting controller to have a direct term. So it has a non-zero D matrix. That gives me 1 sample less delay in the control loop. So that's usually beneficial. Then I take my 2 matrices, L and K, feedback gain and Kalman gain, and create static matrices out of those just for performance reasons. In this case, it's not actually required, but I think it's good practice for a control loop to not allocate unnecessarily. Then I create an observer filter. So that's just a filter that takes the control input and measured signal and outputs an estimation of the state. So this would be kind of a steady state Kalman filter. I create a similar controller, so that would be the observer filter but with a state feedback gain attached on the output. And then I plot a bunch of plots here. Right, there are lots of plots, so let's break those down. Let's see here so that you can see all of them. Yes. All right, let's do like that. So here we see a Nyquist plot. Now keep in mind that this system has a single input, but it has two outputs. So the loop transfer function is either 2 by 2 or 1 by 1, depending on whether or not we have an input loop transfer function or an output loop transfer function. So this is the input version. It's single input, single output. So we can plot that in a Nyquist plot. And we see that it's somewhat close to the critical point here. We see the H infinity norm of the sensitivity function here is 2.5. So we would ideally like that to be a bit smaller. But let's hope that it works anyway. We have a sigma plot here. And here we show the output sensitivity function in red and the input sensitivity function in green. So the peak here of this green curve, the value there is 2.57. And this circle has a radius which is the inverse of that value. So we typically want that circle to be large. We want that peak to be small. Here we have the corresponding plot for the complementary sensitivity function, and here we have amplification of measurement noise, and here we have disturbance attenuation. So the interesting thing we want to look at here is that we attenuate disturbances here for low frequencies, and we do. Here we have a margin plot of the loop transfer function. And since this is an unstable system, we have a fundamental limitation. We must have a crossover frequency that is twice as fast as the unstable pole. And I've drawn that line here, twice the frequency of the unstable pole, and we see that our crossover frequency is exactly around that point. So that should be fine. We see that our phase margin is quite low, 22 degrees is not that high. I happen to know that this controller works very well, so I'm okay with this. The reason we want a large phase margin is because we want to guard ourselves against model errors. And also if it's way too low, we get poor performance. But in this case, we don't need to bother so much with the model errors because it's very easy to try out controllers on this process. I have it here right next to me, and I happen to know that this controller is very robust. All right, in the terminal we have also printed the disk margin. So we see that the margins this gives us is even more conservative. This says that we have a 21.4 degree phase margin, which is slightly lower than the classical phase margin. And this is because this considers also simultaneous perturbations to gain and phase. So by looking at only this, we are perhaps slightly worried that our controller is not robust enough. We have a 3-sample delay margin, for instance. But nevertheless, this is not a particularly safety critical system. We will try to run it. And to run it, I have a script here called swingup. It does swing up as well, but I have turned the swingup off, so it will not do anything unless I manually raise the pendulum up. We will do swingup in a later video. So when I start that, I can put the pendulum up, and we see that it stabilizes there. And I can hit it. In fact, I can hit it fairly hard, and it's still okay. If I hit it way too hard, it does fall down. All right, but this is a fairly robust controller. We can see I can mess around with it like that. All right, so designing an LQR controller to stabilize the problem, the pendulum, it's not too hard. The difficult parts, of course, are to come up with a reasonably accurate model so we can use a model-based design procedure in the first place. Here we see the data. It's a bit messy because I kept hitting the pendulum. But here we see this plot is of the pendulum angle. See, I lifted it up here to around pi, and there is a slight offset here due to a calibration error. I haven't reset the encoder properly. But then we see that it tolerates the fact that I hit it. But then when I hit it too hard, it fell down and it kept swinging, and then I lifted it up again. All right, so that was a stabilizing controller using LQR. In the next video we will also swing the pendulum up. Thanks.